Hello everyone, welcome to this webinar on modeling and analysis of combined pile foundation for silos. My name is Akash Sharma and I work as a geotechnical engineer with FUGRO Middle East based in Dubai, UAE. About me, as I told you, I'm currently working as a geotechnical engineer at FUGRO Middle East based in Dubai, UAE. I have 8 years of experience in the field of geotechnical engineering. My personal interest is in finite element modeling and analysis and its application in field of geotechnical engineering, where I have used it for various applications like shoring, excavation design, pile raft foundation, dewatering analysis, embankment analysis, and others. And I'm familiar with MIDAS GTS NX as well as Plaxis 2D and 3D as numerical tools. And I have issued a few publications again where I have utilized finite element analysis to do value engineering for Barrett Foundation for tall buildings in the Middle East, and also to compare the numerical and analytical studies of 3D effects on pull-out capacity of anchor blocks in granular compacted fill. About FUGRO, as you all know that FUGRO is the world's leading geodata specialist. We collect and analyze comprehensive information about the earth and the structures built upon it. For me, I belong to the FUGRO Geo Consulting team, where we have a group of experts all over FUGRO offices, which includes or covers various aspects of geotechnical engineering, right from site characterization and ground modeling, geohazard studies, earthquake engineering, support during construction and installation, advanced numerical analysis, GIS and data management, even in the field of mining exploration activities, land geotechnical engineering, and others. You can visit our website to check details on this. Moving on. Today in this presentation, basically I will be taking you through a brief introduction to Raft Foundation, the project details, the type of superstructure and the ground conditions we are dealing with in this project, the modeling of various components in MIDAS GTS NX, and then we conclude with the output, what exactly we get from the program and while doing analysis with MIDAS GTS NX. So to begin with, first of all, Raft Foundation. Now we all know that Raft Foundation is an option, economical option, where when in the situation where the performance of the raft alone is not enough to satisfy the design requirements. So under these conditions, we add a limited number of piles to the raft so as to improve the ultimate capacity of the whole system, reduce the absolute settlement as well as the differential settlement, and hence also optimize the thickness of the raft. Based on the recent definition by ISMG Combined Pile Raft Foundation guideline, the Combined Pile Raft Foundation is defined as a geotechnical composite construction that combine the bearing effect of both the foundation element, which is the raft and pile, by taking into account the various interaction between the foundation elements and the subsoil, which is presented in the figure on the right hand side. So you have the pile, you have the raft, and then you have all the interactions which is between the pile soil, between the pile and pile, the raft and the soil, and the pile raft in itself. Now, whenever it comes to the criteria for foundations selection, we all will agree that it is governed by mainly the type of structure, the type of loading which is coming from the structure, what is the magnitude, and how is it's basically distributed, and then the ground conditions. So what kind of soil, whether it's sand or it's rock, what kind of ground conditions we are dealing with. And based on these two important parameters, we decide on the type of foundation. But this is also governed by other criterias, which is, for example, the access of the construction equipment, the durability and the sustainability issues. What is the effect of the installation of the foundation on the adjacent foundation and structures, the relative cost involved, and what is the local construction practices, and because of which what is the availability of the construction material at the site. Now, when it comes to the design philosophy of the pile raft foundation, it is also governed by the serviceability and the ultimate criteria. So the main objective of the serviceability criteria is to ensure that the foundation does not go excessive displacement, and the ultimate state criteria is to provide a sufficient factor of safety against the collapse of the pipe. Now, for most of the application, even the real ultimate state is basically determined by considering the interaction of the foundation and the superstructure. And it basically turns out that the displacement criteria is what is governed after considering the structural considerations. Now, the question arises that why a 3D finite element analysis is required in the analysis and design of pile raft foundation. The first thing is the analysis output, which is required to to understand the behavior of the superstructure foundation system. For example, what is the maximum settlement? What is the differential settlement of the foundation? What are the structural forces in the raft and the pile after considering all the interactions? And this is possible only with the help of finite element analysis. Also, in the preliminary stage of the design, it also provides with the designer to optimize the design. So you understand what is the, based on the pile layout, that what is the relative proportion of load which is carried by the raft and by the piles. And then you can also play around with the pile configuration, which is the number of piles, what is the shape of the pile, what is the length of the pile, the layout, and eventually which will help you understand that which is the most effective when it comes to reduce the absolute settlement, the differential settlement, and also the structural forces both in the raft and the pile. The other important aspect, as we saw by the ISSMG definition, is for a combined pile raft foundation, we should be able to consider all the interaction in a single model, which is between the pile and the soil, the pile and the pile interaction, the raft soil and the pile raft interaction. So in this case, also the finite element analysis is required. Now, after discussing that why the finite element analysis is required, it is very important to understand what are the basic requirements for a numerical model when we are trying to simulate the behavior of the pile raft foundation. The first thing is you should be able to consider the three-dimensional behavior of the pile raft. Now, the constitutive law should be able to consider the nonlinear pile soil behavior at the pile shaft and at the pile base level. The material model which you are using or utilizing for modeling the soil and rock should be able to consider the stress strain behavior of the soil, and which we know that it's dependent on the stress as well as the strain level. So your model should be able to take those effects into account. And always all this design assumptions should be able or should be justified using a pile load test. So your model, so you can model or your model whichever the ground profile and the pile soil interaction, whichever you have modeled, you should always be able to check its reliability with the field pile load test. So you can adjust if needed, or you can be conservative by considering sufficient factor of safety to the applied design parameters. And finally, the applied model, whichever the 3D model which you have considered, should be able to consider the various interactions which governs the pile raft foundations. Now we'll talk about in the project. So the project consists of a superstructure of a group of silos which are used to store rice at the project site. And the overall height of the cylindrical portion of the silos is 18 meter, with the overall till the uh, top of the cone it's something around 23 to 24 meters above the foundation level. The diameter of the silos is 17.8 meters, and since it's in a group, it imposes heavy load on the foundation. So that is why a combined pile foundation was proposed for supporting the group of silos. Now, about the ground conditions, below the foundation level, we have loose to medium dense sand for almost 10-meter thickness, which was underlaid by very weak rock, which is highly weathered Simsima limestone, which is again 10-meter in thickness, and then followed by weathered Simsima limestone. So this is the ground condition as observed by as you can see, the SPT has been plotted, and the SPT ranges from loose to medium dense, that is 5 to 30, and then we have UCS predominantly less than 10, and hence defined as a very weak rock. So initially the piles were designed and the pile length were designed considering the ultimate criteria, and based on that the pile length was calculated for the given working load conditions. So for the working load conditions, which was something around 7,500 to 7,600 kilonewton, a pile load test was also performed to 2 to 3 times the load to check the capacity requirement of the pile. So the pile was 0.9 meter dia pile. I will detail it out in the coming section. So as I said in the previous slide, that whenever you have a design profile and with your pile, with your interface requirement, you should always be able to simulate the behavior of a single pile to check especially the serviceability or the settlement compared to the pile load test. So as you can see that based on our design parameters, so for the soil and the rock, we have used more Coulomb as the material model, which is elastoplastic material. The pile was modeled as a beam element with interface defined between the soil rock and the pile. Initially, we started with 0.67. That's the general practice to define between the soil and the pile, and 0.8 we assumed between the rock and the soil. But later on, we tried to increase the rigidity or our interface between the rock and the soil to 1. And that was our calibrated model. We wanted to have sufficient factor of safety between our calibrated model and the pile load test. And you can see that based on the design assumptions which we adopted, design parameters for the soil as well as the pile and the pile soil interface. At the working load condition, we have sufficient factor of safety. So the pile load test was giving something around 4 millimeters, and we ended up with a settlement of 12 millimeters. So this is the model which we utilized for the modeling of the complete pile foundation. You can also calibrate it further by playing around with the stiffness and strength parameters, but for this project we considered this as our factor of safety. Now we have various components. As we already know, it's a pile raft foundation, so we have a raft and a pile, but we also had feeder tunnels beneath the raft foundation, and it was very important to model them to understand the interaction even between the raft and the tunnel, and the pile and the tunnel, to have a complete picture of how exactly it is affecting our settlement, right? Settlement of the whole foundation system. So we adopted a volumetric modeling for the raft. So the raft was modeled as a solid element, and so was the tunnel. As you can see, the details of the tunnels are provided with the thickness of 0.4 meters and overall width of 3.6 meters. We had 4 tunnels below the Raft Foundation. Now, for the modeling, you can see that it's a big model because of the raft size was also very big. And since we were interested in differential settlement, we modeled all the silos instead of going off half or quarter modeling, which can also be one of the approach. So we selected the boundary conditions such that there is the size of the model such that there is no effect of the boundary on the analysis. Sorry. Moving on to the pile modeling. So the pile initially were designed, as I told you, based on the ultimate capacity criteria with a length of 22 meters. And the diameter was selected, the diameter was 0.9 meter, which is a circular pile. Now, the piles were modeled as 1D element, and the interaction between the soil and pile were defined using an interface element. As I already listed it out, that we considered a rigid behavior between the rock and the pile with R inter, or the strength reduction factor as 1. So the pile were defined as 1D element. Many people do take approach of using or modeling the pile also as 3D or volumetric element, but it's always governed by the amount of analysis time, and hence in this particular project we opted to model them as 1D beam element. Yeah, the next important part is the import of the model from MIDAS Gen. So if you are a MIDAS user, you will be aware that MIDAS Gen is the structural product, which is used for analysis and design of buildings and general structures. So here, in this particular project, the client provided with the stat file. Now, MIDAS Gen has an interoperability with stat and ETABS software. So any model which has been created in ETABS or stat can be imported in MIDAS Gen. And MIDAS GTS NX has a very good feature where you can import the complete structural model in MIDAS GTS NX. So let me just go to the uh, software to demonstrate you how easy it is and how and what all details you can import it. So whenever you go to MIDAS GTS NX, in the import option, let me just open a new file. Let's say okay. So when you say import, there is an option called MIDAS MXT file. Now the MIDAS MXT file is a file which is used as an interoperability format between its various structural and geotechnical software. So what it does is, so when you come here, now I already have exported this file. So in MIDAS Gen, you just go and you export this file where all the load details, I'll show you what all comes with it. Let me import this file inside my inside MIDAS GTS NX. So just give me a couple of minutes, it's trying to import. So what it does basically is, whenever you import any model, it brings with it, it's already imported. So let me show you what all comes. So this is model. So whenever you import any model file, so you have all the structural components. So these are the beam elements, which is basically the piles, which they have modeled in the structural software. The plate element is here, and all the mesh. So even if you have superstructure, so if you have any building or silos and you want to completely import the silos inside the model, that is also possible. Okay. Now you might be thinking that why I need this point spring, which they have utilized it. I will say I'm not going to use it, but what we do is basically we have all the coordinates with us now, right? We have all the pile locations, you have the raft dimensions. You can use the same to generate your model in MIDAS GTS NX, which eases up your process. Okay, and the best part is all the load cases which has been defined. So these are all the reactions. Okay, now two approaches can be taken by the designer. Either you can import all the reactions, all the forces coming from the superstructure on the top of the foundation, or you can also import all the structural component like the silos modeled as plate. But in this, we took the approach of importing the reactions. Please note that there are many load combinations which becomes easier in structural software rather than geotechnical software. So that's why we took the option of importing the loads along with the substructure into the geotechnical software. Now let me go to the back to the presentation. Now how does it helps? First is the geometric modeling. Okay, now let me again switch to the presenter mode. I'm sorry for that. Okay, so the first is the geometric modeling. So even let me go back again to the software. So even when you model anything in MIDAS Gen, you can export a DXF file from there, and you can just import that DXF file here. So instead of manually or creating everything again, you can just utilize the hard work which the structural engineer did to model all the pile locations, and you can directly use it in for your modeling. Okay, so that's a big advantage. It saves a lot of time. And it also helps with the interoperability, like you can bring the reactions from there, and you keep the same mesh number, because you also bring the, so you can see this is the AutoCAD file, so I'm not importing it. So you also bring the mesh set from there, right? So you have all this mesh set. So this node number are similar to what you have in your structural software. So any changes there, any change in reaction, and it's easily you can just import the reaction without manually going and selecting each of the node and applying the load there. You see you have a huge force data which directly comes into the GTSNX software. So this approach was utilized in this particular modeling. Okay. So first, the geometric model can be fully imported. You have the mesh details and the loading details. So you can bring all the loads, as I told you. So the various combination, all the reaction because of the wind load, because of the earthquake load, temperature load on the top of the foundation can be brought as reaction, and you can utilize it as a load combination in MIDAS GTSNX itself. So regarding the meshing, MIDAS GTSNX provides with manual control and advanced meshing tools, meshers, like you have the Tetra as well as the hybrid mesher. So it's always better to, because whenever you have piles, you cannot go for very fine mesh or very small mesh size all throughout the model. So it is always recommended to manually optimize the mesh or do a sensitivity analysis to capture correctly the interactions between the raft pile and the raft soil. I've seen many times people using a mesh size of 3 all throughout the model, and then the contribution from the raft and the load contribution taken by the raft and the pile is quite different, and which doesn't make sense many a time. So you can always have this option of you wherever your zone of concern is, or wherever you understand the stress will be more, you can create a zone, a separate rectangle, then extrude it, then basically divide solids or create solids inside, and then optimize mesh, go for a finer mesh or a smaller mesh size where you understand your pile is and where the stress concentration is going to be more, and you can go for a coarser mesh outside this area, so which helps you optimize the mesh as well as save analysis time. So this you should do to properly get the load contribution and the stress distribution in the model. Now loading and load combination. So as I told you that you have all the load guests set reactions coming as a set reactions, like as I just showed you, you have LDC1, 2, 3, which represents the various load cases defined in MIDAS Gen. Then you can bring it here. You can decide on the most critical load combination. You know that we cannot run for all the load combination as easy it is in the structural software, because here we do a nonlinear analysis. So running for each of the cases is not that easy as compared to the structural software. So based on the initial structural analysis done, you can always decide on the most critical load combination case which you have, which can be the case where you have the maximum reaction on the pile, or the maximum contribution, load sharing contribution coming from the pile. Decide on the serviceability load combination, create the combination in MIDAS GTS NX, and then you can run for the serviceability criteria here in MIDAS GTS NX. So in the construction stage analysis, we define 3 stages where we have the initial stage where we try to initialize the stress condition in the soil, and the second stage we activated the pile, raft, as well as the tunnel, and in the third stage we activated the load combinations where you have whichever load combination. So here what happens is you have 2 stages, and in the third stage you can activate 2 to 3 load combination, and you can keep it overnight and run. So in our case, we also decided on 3 load combinations, which was governed by the maximum force in the pile, or the maximum contribution coming onto the piles, and then we did the check for those load combinations. So after that, we run the analysis, and on running the analysis, if you recall that in one of the slides, I said that why a 3D finite element analysis is required is first we check for the absolute settlement. So you can see that we have a settlement of maximum of 25 millimeters, and you have all the contours, which gives an idea of the differential settlement as well across the silos and across the raft foundation. You get the stress below the raft. So what is the stress below the raft, as well as this is the tunnel sections which you can see. So what is the maximum stress? So we observed a maximum stress of 108 kPa coming below the raft foundation. So one of the most critical aspect was how the tunnel is going to behave under such huge loading, whether it was designed and it was able to take the vertical stress coming from the silo loadings. And we checked and we found that the stresses generated were well within the acceptable limit of the grade of concrete considered for the tunnel. So let me also just move on to the software, MIDAS GTS NX, to show you the model and the various stages and results in the software itself. So this is the complete model, as you can see. So you have the imported model as well, imported mesh set as well. So in MIDAS you can activate, deactivate which mesh set you want to use. Right. So this is the settlement contours. So you can see the mesh optimization. So this is what I was talking about. So mesh optimization you can always do with the separate solid. This is my approach, that I just divide it internal solid so that I can mesh it finer and optimize my meshing, keeping it finer near where I'm expecting the stress concentration to be, and coarser where it's not required, so that I save some time in the analysis. Okay. Okay. So talking about the results. So once you have completed the analysis, you will be able to check all the displacement, the stresses generated. You can check on and check off the various components to check what are the stresses generated in the model and the tunnel. Okay, so the visualization is also quite simple, and you can check in this way what are the various forces generated. Apologies for that. Okay. Now, after that, we also need to check the axial force, which is being generated in the model, and we checked, and you can see that we are getting the maximum axial force at this corner. And for the particular serviceability load criteria which we selected, even the structural analysis was giving the maximum force in the same pile. So you can check what is the maximum force, axial force generated, and check against your ultimate capacity and the working load conditions which you have considered in your design. So finally, you can also check the pile raft contribution. So for this particular project, we have a contribution share of 79% by the piles and 21% by the raft. The maximum axial force was 7,461, which is the working load even initially decided by the structural analysis. And the average bearing pressure below the raft was 110 kPa, which was well within the acceptable limit as provided in the interpretative report. So if you see, I've shown you the various outputs. Now the 3D finite element analysis, this helps and provides you a better insight into the behavior of the complete geostructural system, right? Yeah, you get the serviceability performance of the systems, you get to check the absolute settlement, the differential settlement across the foundation, you check for the capacity check for the stresses generated in all of your elements, whether it's raft, whether it's piles, and of course you can, if you are in the preliminary stage of the design, you can always optimize the design system. This particular project, the analysis was more to check the serviceability criteria, the settlement criteria of the system working under various load combination, and by considering the various interactions between the structural components, which in this case was raft, pile, and as well as the feeder tunnels. Also the soil structure interaction in recent analysis, and you can find various webinars done by the team of MIDAS, that they have an interaction where you can completely bring the superstructure as well and model the soil. And as one of the slide I showed that it's the behavior of the structure which governs the settlement criteria, the amount of forces which are generated in various structural component of the superstructure. So that can also be modeled simultaneously with the construction stage which needs to be considered, and this provides a better insight into the performance of the superstructure foundation system. Now, finally, advantages with MIDAS GTS NX. The user-friendly GUI helps you model anything complex. You have all the inbuilt modeling tools. You need not import everything. Of course, they have very good interoperability even with Excel and AutoCAD file, but they have all the modeling commands in the software itself, the interoperability with the structural software, especially for such kind of analysis where you have to get all the reactions, and it's very difficult to put manually each reactions and pressure load, finding where the node or where the location of column is. It helps to save a lot of time in modeling, as well as uh, provides ease in considering any load combinations which needs to be considered. You have advanced 3D auto mesh options. Of course, manual control is also possible with manual tricks of modeling small solids to help reduce the analysis time further. They have efficient analysis solver. With such a big model, you can run in a and I don't exactly remember the amount of time required, but it was quick enough when you use the GPU acceleration. So you can have a look at the details from the MIDAS team of how you can accelerate the analysis time using the GPU acceleration. So that also helps save a lot of time. So this is all from my side. I hope I was able to give you some insight about the modeling and analysis of the Raft Foundation using MIDAS GTS NX. And if you have any questions, kindly let me know. Thank you. Thank you very much.